Okay, good morning, everyone. Today we'll wrap up AC power. Okay, we only have one more slide on the theory and the concept, and then we have the two examples. In order to save time, already have my handwritten annotations in the class notebook. If you open those up before class, you would have seen that both the examples have the solutions on there. But I will go over everything and explain in detail. So let's go ahead and open up the class notebook. I'll do a brief recap of the three slides. Okay, there we go. Okay, so I introduced the topic of reactive power last class. Reactive power has to do with the reactance of the inductor and the capacitor. And in real life, most of the loads in an industrial environment are inductive loads, and so they require reactive power. Now, mathematically, we represent that reactive power using the imaginary number, the same way we represent reactances with an imaginary number. But it has a physical basis in real life. The utility company has to send high voltage and high currents associated with the real power as well as the reactive power. And so the equations associated with this reactive power, again, described using the complex numbers, show that reactive power Q I forgot to plug in the USB. There it works now. Okay, so reactive power Q represented with the imaginary number J and added summed up with the real power P gives us the equation for a total complex power for a system. And that is represented by S equals P plus JQ. Okay. Reactive power for an inductor is positive. Reactive power for a capacitor is negative because the voltage for an inductor leads the current, whereas the current leads the voltage for a capacitor. Okay. And then we describe the current in terms of the voltage by a term known as the power factor. Okay, power factor. Power factor describes whether the load is inductive or capacitive. Okay, power factor describes whether the load is inductive or capacitive. If current I leads the voltage, then power factor is said to be leading. If current I lags the voltage, power factor is said to be lagging. Okay, so the reference is the voltage, but it's describing the relationship of the current with reference to the voltage. If you need help remembering, you can use this mnemonic. Eli Manning came up with this. Not really. L stands for inductor, C stands for capacitor, E stands for electromotive force, another term for voltage. So for an inductor, the voltage comes before the current, meaning the voltage leads the current. In other words, the current lags behind the voltage. For a capacitor, it's the exact opposite. The current leads the voltage, or voltage lags behind the current. For a power factor, we are describing the relationship of the current with reference to the voltage. If current leads, then it's a capacitor. Hence, we say power factor leads, or so power factor is leading. If current lags, then we say power factor is lagging. In most industrial environments, have an inductive load, or inductive loads. And so power factor for an industrial environment or an industrial consumer is always lagging. Okay, power factor is always lagging. Quantitatively, that power factor is given by the cosine of the power angle. Okay, theta is the power angle. It's the difference between the phase of the voltage and the current that was mentioned in the previous slide. Okay, theta is the power angle. It is the difference in the phase between the voltage and current. So theta V minus theta I, and the cosine of that power angle gives you the power factor. It is typically described as a percentage. Okay, if it's a purely resistive load, there is no phase difference between the voltage and the current of a resistor. So the power angle theta is equal to 0, which means power factor of a resistor R would be equal to cos 0, which would be 1. In terms of percentage, it would be 100%. Okay, 100%. For typical inductive loads, power factor would be anywhere, could be 50%, 40%, 30%, depending on the inductive load and the circuit configuration. What we need to do is to balance out the requirement of this inductive reactive power by applying a bank of capacitors or installing a bank of capacitors in front of the inductive loads. And as we saw in last class, when you connect a capacitor in front, it reduces your requirement for the total reactive power from the source. And that is known as power factor correction. Most utility companies will not supply electrical power to an industrial consumer if their power factor is below a certain point. And I'm just guessing here right now, maybe PG&E or any other utility company will not supply electricity to an industrial consumer if their power factor is below 90%. Okay, they would contact the customer and say, you need to bring your power factor up above 90% or 85%, depending on your installation. So let's say bring your power factor up above 85%, otherwise we will not supply with electricity. And so L plus C, or inductor plus the capacitor, is known as the power factor correction. Okay, power factor correction. So the calculation and the installation of the capacitors to balance out the inductive power requirement is known as power factor correction. It reduces the amount of reactive power that would be required from the utility. The other equations associated with the power are given by the RMS values of the current and the voltage. So for a resistor, it still remains the same, obviously. P is I squared times R, or V squared over R. That's the format, right? I squared times R, or V squared over R. Except that this time you're talking about an AC applied voltage or AC applied current. So when it's AC, we use the RMS values for the current as well as the voltage. But the form of the equations still remain the same. It's the exact same equation that we saw in chapter 1. Okay. In terms of reactance, we can describe the reactive power using the same equations. I square RMS times X and V square RMS divided by X. And this could be for both inductor and capacitor. Okay, inductor and capacitor. Total complex power can also be given by this equation, which is half VI asterisk. Okay, half VI asterisk. That asterisk denotes that is the complex conjugate of the current I. And we will see that, I will show that in the next example. Okay, the complex conjugate of the current I. So this total complex power mostly relates to the entire system, basically the source that is supplying the total complex power. Okay. All right, let's take a 10-second pause. Any questions? That's the asterisk that denotes that it's the complex conjugate of the quantity. Complex conjugate, basically in polar coordinates, the asterisk or the star, if you will. Yeah. Flip the sign, rotates around the x-axis. In rectangular coordinates, if it's a plus jb, it becomes a minus jb. Yes.
Given that a voltage is like polar or complex form, in the RMS.
In here, you take the magnitude and find the RMS values. RMS, the relationship still remains the same. RMS is the root mean square value of the peak value of the waveform. Peak value is given by the magnitude. And so that's the length of the vector. And I'll point it out in the example. All right, any other questions? Okay, let's take a look at the example. So we have two examples. The first one is a simple RLC circuit. The RLC circuit, the values are given to us. The resistor, inductor, and capacitor have certain values. The source value is given to us, and we are asked to find power for every component. Okay, determine the power for every component. First thing I always tell students is they're trying to solve for an AC analysis, meaning an AC voltage or AC current, is to draw the equivalent impedance diagram, meaning we represent every component in there using its complex equivalent. So equivalent impedance diagram means all the three RLC components are replaced with their equivalent impedances. So inductor and capacitors are represented with ZL and ZC. Okay, ZL and ZC. And then, of course, resistor R remains the same. Current I is the total current being supplied by the source. IR, IC are the currents respectively for the resistor and the capacitor. Inductor current IL is, of course, the exact same as the total current I being supplied by the source. Okay. So now, if you think back to chapter 2, at the beginning, we learned a technique called series parallel analysis, right? Where we take a circuit with a large number of resistors and reduce it down to one single equivalent resistance. And so that is the technique that we would use here. Okay, we have a voltage source being applied to a series and parallel connection of three components. So after drawing the first step, the next step, I can see that the resistor and the capacitor are in parallel. We obviously cannot combine a resistor with a capacitor, but what we can do is combine the impedances of the resistor and the capacitor together. So R would be in parallel with ZC. That would give me a component, and I labeled it as ZRC. Obviously, that's a personal preference. You can use any notation you want. That parallel combination of ZRC is in series with the impedance of the inductor, which is ZL. And hence the total ZEQ, the total equivalent impedance of the circuit as seen by the source, is ZL plus ZRC. It's the same as finding REQ for a simple resistive circuit. Okay, as a simple resistive circuit. So ZEQ is ZL plus ZRC. The next, I would represent the voltage source by its phasor equivalent. So 10 sine 1000t expressed in the cosine form is 10 cos of, again, remember, sine x is cos of x minus 90. You need to subtract 90 degrees from the phase angle. So 10 sine 1000t becomes 10 cos 1000t minus 90 degrees. From this, I can extract information. This is omega, this is Vm, and this is the phase angle theta. I can write the phasor for the voltage source Vs directly from this expression. Magnitude 10 with a phase angle of minus 90. 10 with a phase angle of minus 90. Again, the goal here is I want to perform analysis on a circuit for an AC source, right? We use complex math, complex numbers to represent both the impedances as well as our sources. So the source is represented as a complex number, magnitude 10 with a phase angle of minus 90. Then we go to the impedances, apply our equations for ZL, ZC, and ZRC. Okay. So ZL, rectangular coordinates, is J omega L, right? Or omega L with a phase angle of 90 degrees. For a inductor and a capacitor, always remember, impedance of an inductor is the phase difference between the voltage and the current. It will always be plus 90. For a capacitor, it will always be minus 90. So J omega L gives me J100 in rectangular coordinates, or 100 with an angle of 90 degrees in polar coordinates. Same thing with ZC. ZC is 1 over J omega C, gives me minus J 100 ohms, or 100 with an angle of minus 90. I'd like to point out that note taking is very good. It's a good skill to have. But if you try to take notes here, we will never get through the example. So again, I'd like the annotations should be available at your end in the class notebook. Okay, to all students who have signed up. My annotations will be available to you. It should be available already. If you try to take notes, you're not going to be able to follow the explanation. So I would suggest that you follow the explanation rather than trying to take notes at this time. So again, recapping the steps, we are representing all of the components by their complex equivalent counterparts. So the components RLC are represented by the complex impedances. The source is represented as a phasor. All of them are vector quantities. They have magnitude, and then they have phase angles. Okay. ZL and ZC are found as J100 and minus J100. Then I want to find ZRC, the parallel combination of the resistor and the capacitor. Parallel combination of two resistors or two impedances in parallel is the product of the two divided by the sum of the two. And so it's R times ZC and divided by R plus ZC. At this point, if you have a programmable calculator, you can directly go from this step to this answer. Or in case of rectangular coordinates, this answer. I do not have a programmable calculator and I need to perform a division, right? I'm dividing RZC by R plus ZC. So if you do not have a programmable calculator like mine, like I don't, then I want both quantities in polar form. So I transform the denominator, which is 100 minus J100, into polar coordinates, 141.42 with an angle of minus 45. Once again, if you have a programmable calculator and you're confident in your skills, you simply program this equation and you skip to the final answer. Is that clear to everyone? You do not have to show me the intermediate steps. But again, you better be confident in your skills to obtain the right answer. Because if you make an error anywhere, you enter a plus sign instead of minus, or you make an error in entering the complex quantity, your final answer would be incorrect. So just be sure. So then we obtain ZRC. That takes us to this step. The final step after this to find ZEQ is adding ZRC and ZL. So if I find ZEQ by adding ZL and ZRC. Similar to chapter 2, reducing the entire circuit down to one single impedance. Once I add that, I obtain 50 plus J50 ohms, or in polar coordinates, magnitude of 70.71, phase angle of 45. The reason I want it in polar form is because I'm about to perform a division, right? I want to find current. V equals IZ from Ohm's law. And so I equals total source voltage Vs divided by ZEQ. That gives me a current of 0.1414 with an angle of minus 135. Let's take a 10-second pause. Think over the steps. Let me know if you have any questions. So far, we haven't gone into power yet. We are still setting up. You can say it's half the solution, but we are still like kind of setting up before we actually get into the equations for the power. Okay, all we have done at this point is perform resistive analysis. Combine all the components as one, found the currents and the voltages. Does the procedure make sense? Okay, the analysis portion is not new. Just something we did at the beginning of the quarter. It's the math applied to it that is new. Any questions? Okay. So now that we have the value for I, we can find the voltages for the resistor and the capacitor. We can find the voltage for the inductor. We can find, we found the current for the source, which is the same current for the inductor. We can find the current for the resistor and the capacitor, or we can use the voltage. Doesn't really matter which path you take, right? If you find the current for the resistor and the capacitor, you can use I squared times X to find the reactive power. If you use the voltage, you can find for both resistor and the capacitor using just one equation. Because they're in parallel, they share the same voltage. So if you find the voltage across ZRC, you can use V square over R or V square over X. Think on that for 5 seconds. We want to find the power for every component. That means we can use either one of these two equations. Okay, think with me. We can use either one of these two equations, either V square over R or I squared times R. Now, for a resistor, it's R, of course. For a capacitor and the inductor, it's V square over X or I squared times X. meaning we need the voltage or the current for that inductor and capacitor. We already have the current for the inductor because we found the total current in that circuit. For the source, we already have the voltage. If we find the current for the source, we can simply apply VI asterisk and we can find the answer for the total source power. Does that make sense to everyone? Yes. X is the reactance. X is the reactance mathematically without the number, without the imaginary number J. Z impedance is J times X. Okay, impedance Z is J times X. Are these two options clear to everyone? Does that make sense? Okay. Yes, did you have a question?
No, but
No, filters were not on the final. This will be on the final. That's why I'm taking my time going through the explanation. Let's see, where was I? Okay, so we have four components, right? The source, the inductor, the resistor, and the capacitor. The source, VI. That's the only equation we can use. Product of the voltage and the current. Voltage for the source is given to us. We found the total current, so we can apply the VI equation and find the power for the source directly. For the resistor, again, we found the we haven't yet found the voltage or the current. For the inductor, the current is the same as the source. The current is the same as the source. So if we found the I for the source, that's the same for the inductor. So for inductor, we do not need to find the voltage. Makes sense, right? We do not need to find the voltage. We can simply use the I squared times X equation. For the resistor and the capacitor, they are in parallel. If we find the voltage, across those two nodes, it will apply equally to a resistor as well as the capacitor. So again, we do not need to find two separate currents. We can find one single voltage and we can find the power for both components. So when you're trying to solve this problem, think logically. There is no right or wrong approach, right? Both approaches will give you the same answer. And I'm going to show both approaches here. I have both of them written down, okay? But as an engineer, when you're working, want to use the most efficient process, right? And so in this case, we simply find the voltage. All right, so voltage across the resistor is the same as the voltage across the capacitor, simply given by I times ZRC. Remember that total current I is flowing through the inductor, the source, as well as the parallel combination of R and C. So VRC is simply I times ZRC. You can use Ohm's law and find it that way, or as I've shown here, you can use voltage division and find it that way. Just to illustrate two different paths, you'll get the exact same answer. You can practice this, and you should obtain this exact same answer. Okay, I have used voltage division. Then IR, just because as I said, I want to show the other approach. You can find IR again from Ohm's law, and you can find IC again from Ohm's law. You find both the resistor as well as the capacitor current, and you can find the power for each component that way. Okay. At this point from here, you can simply apply Vrms square over R and Vrms square over XC. So this will give you power for the resistor PR. This will give you QC. Okay. Again, practice this for the final. Mentioned this on the first day of class. The final exam topics were listed since the beginning of the quarter. I remind you that AC analysis and AC power are both guaranteed to be on the final. It's been there since the last 10 weeks or 9 weeks. Okay, so using V square over R, you get 0.5 watts. Actually, you don't need to practice, it's already there. And I square times R also gives you 0.5 watts. Same answer, no difference. Practice this. Find VL, right? VL is something I've not found, but VL is simply IL times ZL. IL is the current I. ZL we already found. So practice finding the inductor voltage VL. Find VL, apply to this equation and find QL. QL using the current I squared times X gives me 1. Unit is VAR. Remember, Q units are not the same as watts. They are VAR, volt ampere reactive. Okay, volt ampere reactive. Because impedance of a inductor has positive, right? Reactance and impedance of a inductor is positive. Reactive power is noted with a positive sign. For a capacitor, it's the exact opposite. We put a minus sign in front of the reactance. We put a minus sign in front of the impedance, minus sign in front of the reactive power for a capacitor. So QC is going to be minus, right? It's pointing straight down. Here is the answer to your earlier question. Voltage across that capacitor had a magnitude of 10. Magnitude of 10. Magnitude would be the VM, the peak value. To find the RMS value, we divide by √2. So that's what we're doing here. I want everybody to make a note of this. Do not use the magnitude directly. Anytime you use the equations V square over R or I square over R, it has to be the RMS values. The RMS value, again, chapter 5, is still √2 times, peak values are still √2 times the RMS values. So RMS values is the peak value divided by √2. So you had the time varying expression, 10 sine omega t, had a magnitude of 10. That magnitude is still the peak value. To find the RMS value, you divide by √2. Hence, 10 divided by √2. Same thing with the current. The current we found as 0.1. RMS value of that current is also 0.1 divided by √2. I squared times XC. XC is noted with the minus sign. We get minus 0.5 VAR. And there we found power for every component except for the source. And the source would be simple because source is given by P plus JQ. We found P, and we also found the total Q in the circuit. Sorry, we found the Q for every component in the circuit. To find the total reactive power supplied by the source, we simply add up all the Qs. So that would give us 0.5 plus J0.5. Inductor requires 1 VAR. Capacitor provides half of that. So the total reactive power required from the source is now dropped by 50%. Take some time and think about it. Let me know if you have any questions. Yes. 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 P plus JQ. Yeah. All of the equations that student would need are in these 2 slides preceding the examples. So all of those are in there, and you can have them in your equation sheets, of course. Yes.
The negative on the 100 for the QC. You just knew to put that in there, right?
Yes. Yep. Yep. That's why I wanted the students to pay attention and not, just look at notes. QL is positive, QC would be negative. react, and that comes from the fact that the current leads the voltage for a capacitor. So when you find the complex impedance, phase angle of voltage minus phase angle of the current gives you a negative phase. So impedance for a capacitor will always be minus 90. Impedance for an inductor is always plus 90. Same translates over to QL and QC. QL is always positive. QC is always negative. The other way to, any other questions before I show the other approach? It's a lot to take in. So again, review this right after class so that it doesn't fade from memory. The other way to solve this would be to use the equation S is equal to P plus JQ and find real power P and reactive power Q using the equations VRMS, IRMS cosine of theta and VRMS, IRMS sine theta. These equations were on that first slide, and I wanted to wait until to bring it up. These are right here. Remember, these equations apply to every component. Okay, these equations apply to every component. You can use these equations for R, L, and C, but a resistor does not have Q. Resistor does not have Q, does not have reactive power. And a capacitor and an inductor does not have P, real power. They only have Q. So if you have the voltage and current for any component, you can apply these equations and find the power, the real power P or the reactive power Q for that component. So we could use these equations to find QL and QC also in this example. That is also another way to practice finding QL and QC. Okay. This is just for the source. So for the source, the voltage and the current, the voltage was already given to us. We found the current. The power angle is 45 degrees, V minus I. And so then I would simply plug in the RMS values of the voltage and current and find P and Q. Again, this is just for the source. Once you go through that, you can see the values match up with what we found in the previous step. Okay. 0.5 watts and 0.5 VAR. Again, to get a better grasp of these equations, better grasp of the fundamentals, you can use these equations for the resistor, inductor, as well as the capacitor, because we found VL, we found VC, we found IL, and you found IC. You can apply these equations, VRMS, IRMS, cosine theta, and sine theta, and find P and Q for each component. If you plot this, this is the power triangle for the source. Okay, power triangle for the source. These are the power triangles. This is for the source. Well, this is also for the source, actually. This is just an explanation of what happens. QL, if this is 0, this is 0, QL points straight up, right? QL points straight up. If these were two resistors, they would add up linearly, right? Two resistors, meaning one resistor has 1 watt requirement. The second resistor requires 0.5 watts. Then it'd be 1 plus 0.5. We are doing the same thing here. We are doing QL plus QC. But because they're complex quantities, we have to take the phase angles into account. QL points straight up. And instead of adding QC going up, QC actually points down. So the total power required total Q is reduced. So it becomes 1 minus 0.5. Make sense? Yes.
That's the back and forth element of the reactive power.
Yes. Yep. One final approach is also using the complex conjugate equation. Remember, P, power, electrical engineering, is the product of the voltage and current. For complex power, total complex power, it is half VI asterisk. Okay, half VI asterisk. Do you guys call it asterisk or do you call it star? Either one. Okay. Asterisk is a little harder to pronounce and say. Maybe I'll stick with star. Anyways, half VI, the equation, where is that star, that asterisk, notes that it is the complex quantity, complex conjugate of that quantity. And complex conjugate of the current I means that that minus 135. Remember, we found the total current I here, and the angle was minus 135. The complex conjugate simply removes that minus sign, not removes, but flips that minus into a plus. And so it becomes 0.1414 with a phase angle of plus 135, which is right here. Add it up, you get the answer in polar coordinates. When you transform that answer from polar to rectangular, you obtain the exact same answer, 0.5 plus j 0.5. When you equate this with S is equal to P plus JQ, P is 0.5, Q is 0.5. So we can use multiple equations, multiple approaches, and yet arrive at the exact same answer. Okay, we found the total complex power for the source in 3 different ways. Okay, in 3 different ways. So again, here, showing you what the complex conjugate does. All right, so that was total complex power from there, from these equations, and then of course from the component values. All right, think on this. Let me know if you have any questions. It is 9:54 or 9:53. So what I'm going to do is, I do have another example after this, but I'm inclined to not include that on the final exam. So this is power factor correction. This is another way of trying to find the power for a system. But again, in the interest of, well, best interest of the students right now, I think it's a lot of information trying to find the AC and trying to do the AC analysis and then find power for every component. Not include slide number 8 or page number 8. Consider it as outside of the syllabus, but go through the example. It'll help and aid your understanding of the previous example. Okay, go through example 2. The steps are all listed. There's explanation also listed. It's rather straightforward. And then it will aid and help your understanding over example number 1. Okay, so let's go back to example number 1. And then I'll do a quick recap. Okay, we are given a RLC circuit with an applied voltage source. We're asked to find power for every component. It's kind of like a 2-in-1 problem. To find the power for every component, we need to find the voltage and the current for every component. We can use the equation from either voltage or current. We can use V squared over R, or we can use I squared times R, or V squared over X and I squared times X. Same equations. So we reduce the circuit. we first drew the equivalent impedance diagram, reduced the circuit to one single equivalent impedance, found the total current I by applying Ohm's law, ZL, ZC, and total ZEQ, found the total current I. Once you find the total current I, you can find the current for the capacitor and the resistor, or you can find the voltage. We found VR. VR is the same as VC or VRC. Then we found the current for the resistor and the capacitor. Then we applied our equations, I square RMS times X, and then I square RMS times R. So I have shown both approaches here, 1 and 2. Okay, you will still arrive at the same answer. As an engineer, it's your choice on which approach you wish to use. And then simply add it all up using the expression S is equal to P plus JQ. That would give you the total power in the system, which is being supplied by that source. To find the source power, you can also use two other approaches, which are shown right below. Yes. Yeah, it's the right here. So this is ZL, which is JXL. ZC is 1 over JXC. And so the J or minus J is basically the phase angle, 90 degrees minus 90 degrees. And so it's magnitude of the impedance, 100 ohms. Yeah. Again, reactance is the same, has the same units as the impedance. Right? Reactance, impedance, and resistance, they all are described as ohms. Chapter 5, I think, the last few slides. Okay, other questions? Yes. When? Oh, that's just the equation that we're using. We're not getting rid of the complex aspect of it. We are simply using the magnitude of that impedance, which is just the reactance. Yeah. Almost out of time, but I always have time for questions. So we'll end class here today. And then on Friday, I'm going to have like an open office hours kind of thing in the class. So if students have any questions from the beginning to the end, from the beginning of the quarter to the end of the quarter. Okay. I'll be here, whether anyone shows up or not. The Zoom session will also be on. So if you have any questions, prepare them well, and we'll have an open office hour during class time. No, I just assume that there is. I'll send out an email later today, but there's plenty of space. So one other thing I wanted to show is great job on the response rate. I think this section is by far the, where's it gone? It's okay. So right now we are at 56%. So every student in the class gets 0.56 points towards their overall grade. And then there's still a couple of days left. Hopefully the response rate will go up. And if it goes up, again, your extra credit points go up also. Okay, so great. Good job. Is it? All right.